Hello and welcome. My name is Shane Jansen and today we'll be talking about my senior project, which is going to be active aerodynamics for a 2010 MazdaSpeed3. To start, a little bit of a background on what active aerodynamics actually are. Active aerodynamics are self-adjusting aerodynamic components of a car. These are typically actuated based on the vehicle speed, your steering input, and braking input, depending on the application. These systems are used to improve fuel economy and/or performance numbers, again depending on application. They can decrease drag, increase downforce, or increase airflow to components that need it, much like intercoolers or radiators. Typically, these types of systems are exclusive to high-end luxury and performance cars. I think the primary reason for this is because of reliability concerns and cost effectiveness, though these technologies are beginning to trickle down into some everyday cars. There's a number of different types of active aerodynamics, including things like front splitters, air dams, rear spoilers, and more. Front splitters can do things like increase front downforce or reduce drag. They do this by either extending straight out from the bumper or lowering beneath the bumper. Air dams can help to redirect air where it's required most, whether that be to cool brakes or to be rerouted to your intercooler, radiator, and other components. Rear spoilers can be used to increase downforce. They can be used to reduce drag for helping reach a maximum velocity, or even increase drag to help decrease braking distances. An example of this can be seen here in the picture above. This is a McLaren 675 LT using its rear air brake to help slow it down. The goal of this project is to apply active aerodynamics to my personal vehicle, which is a 2010 MazdaSpeed3. What I'm hoping to get out of this is an increase in the amount of downward force on the rear axle while it's in the fully down position, and an increase in the amount of drag under heavy braking when it's in the up position. This will hopefully stabilize the rear axle of the car under heavy braking, as well as force the rear brakes to do a higher percentage of the braking. As most people don't know, your rear brakes only do a very small percentage of braking when you're stopping a vehicle. Your front brakes do most of the work. This will also effectively function as an air brake. If you can imagine, like this diagram here, it would just be a matter of flipping this upward at something like a 55-degree angle. I've been doing a lot of research on how these systems work, and every car is a little bit different. Cars like this Ford GT down here in the lower left use hydraulic cylinders to raise the rear spoiler. Other cars use pneumatic cylinders, and some others electronic linear actuators. Electronic linear actuators are the way that I plan on going for this project. I found several DIY projects online, mostly through YouTube, that use electronic linear actuators to raise the rear spoiler. An example is this R53 Mini Cooper. This was a project done by a gentleman named Anthony a few years back. He's got two linear actuators here that raise the rear spoiler every time the brake light comes on. This is a lot like the method that I plan on going with for my project. I expect to face a number of different challenges throughout this project. To begin, the lack of mounting options and locations. As much as I'd like to maintain the original mounting locations as the original spoiler, I don't know if that'll be possible. I'd like to really avoid drilling any new holes in the car. Of course, the whole system needs to be weather resistant. This car will see temperatures high and low, it'll see rain, it'll see snow. This car never sits in the garage. I'd like the wing to change from its lowest position to its highest position in less than 2 seconds overall. I'd also like to minimize the overall amount of weight added to the vehicle, as every ounce counts when you're trying to go fast. I'll also be installing an on-off override switch. This way the wing isn't flapping up and down in stop-and-go traffic. I'd also like to get this project to cost me less than $400, which I think should be possible, but we'll see how it goes. I'll be using a wide range of different components and materials for this project. For the body of the rear wing, I hope to use either fiberglass or carbon fiber composite. This will be dependent on the design choice that I go with at the end. I'll be using linear actuators to get the movement that I desire. Of course, I haven't chosen the manufacturer yet, as I still need to figure out which one is best for my application, as they must be weather resistant and have a good balance of speed and force output. For the mounting hardware, I'll be using a mixture of machined aluminum, 3D printed PLA or ABS plastic, and stainless nuts and bolts. Again, primarily just to prevent corrosion later on down the line. This right here is an example of a linear actuator. This one's a little bit longer than what I'll probably be using, but it basically functions the same way as a piston. I'll be applying a broad range of knowledge that I've learned throughout my last few years of school to this project. I'll be applying knowledge that I got from classes such as manufacturing processes, solid modeling, dynamics, fluid mechanics, CAM fundamentals, and I'm sure I'll find a few more along the way. Of course, I'm a transfer student, so a lot of the knowledge that I'll be applying not only came from Alfred State College, but also from my time at Morrisville State College. I hope to finish all my research and design no later than February 11th, 2019. After that, I'll be doing some simulations and data collection through SolidWorks to see which design works best. I'll have that done by February 18th of 2019. After that, it's time to find all the materials that I need and actually put everything together. I'm giving this a large chunk of time, and I'm expecting to complete that by April 1st, 2019. After that, it'll be time to mount the completed project. I'll finalize its appearance and do some initial testing to ensure that it's functional. I'll have that done by April 15th of 2019. I'll do some real-world testing after that, and I'll have some real-world testing and data collection done by April 22nd, 2019. That real-world testing will hopefully include not only driving on the street, but maybe some track time at Watkins Glen International. Lastly, I'm expecting project demonstrations and the end date of this project overall to be on April 26, 2019. So what progress have I made so far? Well, I'm continuing to do research as I'm learning a lot with this project. I've already reached out to a number of people, including the gentleman who owns the Mini Cooper that you saw earlier in the slideshow. I was able to find a 3D model of my car which I can manipulate and test designs on. This is what I'll be putting into SolidWorks to see which design is best. I've also thought of several different design approaches. I'm not sure which one I'll go with yet. That'll depend on which one works out best in SolidWorks during simulations. Thank you everybody for watching. That's the end of the presentation. I can't wait to get to work and see how this project comes out.